Welcome to Pre-Calculus. Today we will investigate solving triangles using the law of cosines. We'll take a look at three examples. Our first example is a triangle, and clearly this is an obtuse triangle. It's got one angle that's bigger than 90, and the information we have involved two side lengths, 8 and 17, and an angle measure that comes in between them, 43 degrees. And our goal here is to solve the triangle. So remember, when we say solve the triangle, it means I want to find all the side lengths and I want to find all the angle measures. So for us, that really amounts to three things that we want to find. We want to find this missing length of side BC. And then we also want to find the measure of angle B and the measure of angle C. So we've been looking at different results from trigonometry that would help us to do this task of solving a triangle. We looked at the law of sines. We want to introduce a new law here. It's called the law of cosines. And in fact, the way the law of cosines works is it's really the general form of the Pythagorean theorem. And it really appears in three different ways. So let's list the three different ways that we see for the law of cosines. And this version, in fact, these three that we're going to see are good for this arrangement where I have a side, an angle, and a side, and that angle falls between the two sides. So I'll just write SAS there for side, angle, side. So the first version that we might see is going to be this one. A squared equals B squared plus C squared. So that's pretty familiar to us from Pythagorean theorem. This is the part that's new for law of cosines, minus 2BC times cosine of angle A. And that's the new part, and that's why we call it the law of cosines. It involves cosine. One thing I'd like to just note here is that the B squared and the C squared, whatever's squared on this side, those same variables are going to show up in this added term. So this one's minus 2BC cosine A. The other thing to note with this formula is that this A squared will match this angle A. So that's one version of it. Let's give the other two versions so you can kind of see how they're related. B squared equals A squared plus C squared minus 2AC times cosine of B. Again, just to see this for its patterns, again, my A and my C, since those are the squared terms, are going to show up as my two factors there in the minus 2AC. And then I'm also going to have B matching up with the angle. So the side and the angle will match. So just using that pattern, you can probably predict this third version. C squared equals B squared plus, in fact, I should probably put A squared first just to keep it alphabetical. A squared plus B squared minus 2. See if you can predict it. Good. AB times cosine of angle C. And that's really our go-to if the type of information I have on my triangle involves two sides and the angle that falls in between them. Now, I do want to select one of these to start with. What we do is we match it up with the information that I have in the diagram. So I'm going to go over to the diagram here and label what I've got. I know I've got angle A. I'm going to mark that angle there. And then recall the side opposite angle A is side A. So that's really what I'm looking for first. Here's angle B. Opposite angle B is side B. So that's got a measure of 8 feet. We would also call that side AC. And then angle C, the obtuse angle, opposite it is side C. That's 17 feet in measure. So to start with, I want to find side A. I can see that's the side that's missing. And I'm just going to select the equation that starts A squared equals so forth. Now I do need two sides. So B and C, I need to fit them in here. So let's set up our equation for this triangle. It's going to be a squared equals, so I'm going to plug in for B 8 feet squared plus C, which is 17 feet squared, minus 2. And then remember, we repeat those lengths. A is length of 8, C is a length of 17, times cosine of angle A's measure is 43 degrees. And that's really ready to evaluate. The only thing I need to do here is take the square root. Again, I don't really want just a squared, I want a. So we'll let that square root pass through that c. That's the expression I want to input into a calculator to get my side a. So we'll put a equals about, because it's going to be an approximation. And we'll take this over to our graphing calculator to evaluate. So I'll start with the square root of 8 squared plus 17 squared minus 2 times 8 times 17 times cosine, and our angle was 43 degrees. One thing you do need to check, whatever calculator you're using to make the calculation, is that it's set to degrees. So here on Desmos, the way to check that is here at the graph setting, that wrench in the upper right, and radians, degrees are located below. So I'm going to click degrees, and that ensures that we're getting the right calculation. That's 12.4. We'll head back to our note screens to finalize that distance. So A we have is a length of 12.4 feet. So in terms of solving the triangle at this point, if I put that A there, 12.4 feet, we've got all of our side lengths. Go ahead and highlight those. So I know that 2 of them were given to me already. B was 8, C is 17. Now I have A is 12.4. So what's left for us to solve now is the 2 angle measures that are missing, angle B's measure and angle C's measure. So if I'm looking for an angle, I really want to use kind of a modified version of the law of cosines. So let me give the modified versions here. And this is something that you might use in a different setting if you had all the side lengths, but you didn't know any of the angles. We're going to use it here once because I've got 2 missing angles. But if you're missing all 3, you could use this version. So it's really set up for if you have all 3 side lengths. So I'll put side, side, side there. And let's list those 3. So again, it starts with the first version, cosine A. And what that would equal, it's basically this first one that we've already used solved for cosine of A. So just to imagine how that would work, I've got B squared and C squared here already. What we would move is A squared over to the right. So B squared plus C squared minus A squared, all divided by 2BC. We have 2 other versions, so you can imagine how they relate to this one, cosine of B. And the way cosine of B would look, and that's that second formula, it's going to be A squared plus C squared minus B squared over 2AC. And then our last version would be cosine of C, which comes from this third version solved for cosine C, and it would be A squared plus B squared minus C squared over 2AB. So again, there's 3 different versions. You don't necessarily have to have those. I could use one of my 3 originals, but these are convenient if I'm trying to solve for an angle. So for us, let's start with angle B. So I'm going to choose that one that involves cosine of angle B. And I'll set it up the way that it is right here. So I don't know the angle. I'm going to just write cosine of B equals, and then I'm going to leave a gap for an operation we've got to perform in just a moment, but let's fill in a squared, c squared, and b squared. So it's going to be a squared, that's 12.4, plus c squared, which is 17 squared, minus b squared is 8. And that's all over 2 times a times c. And that's going to be 12.4 and 17. So again, that's the setup if I wanted to know just cosine of angle B. I don't really want cosine of angle B though, because I really want the angle measure. So recall from our work in previous lessons, I can access the angle measure by applying the inverse cosine function. So I'll apply it on the left. It'll cancel out cosine and just leave B. And my angle measure is going to come from this expression, inverse cosine of that fraction. So just like with our first calculation, we want to take this to the calculator. And we'll input this in. So to find the inverse cosine, I'm going to find the keypad, functions tab, and inverse cosine's in the middle column, second down. Once I've got that one, I'm good to set up the rest of the fraction. We'll just expand it so you can see it. So it's inverse cosine of the fraction. Again, as we set it up, 12.4 squared plus 17 squared minus 8 squared all over 2. And if you forget, it's times these first two, 12.4 and 17. And that's calculating for us an angle, which is 26 point, if we round to the 10th, 26.1 degrees. And again, we had already checked to make sure that our calculator was set in degrees, so we're good. And we can finalize this calculation. The measure of angle B is about 26.1 degrees. So just again, taking stock about what we'd solved for, I've got all three sides. I have two of my angles, and all I need is a third angle there. And there's different ways we could find the third angle. The most direct way is just to remember that in a triangle, all three angles add to 180. So to find a missing angle, we just have to take 180 and subtract the two angles that we know. So we can set it up that way. And what that's going to give us is an equation like this. So we would say the measure of angle C, that's that third angle, the obtuse one, is going to be 180, which would be the total of all three if I added it up, minus the two angle measures I know. So minus 43, and then minus the one we just found, 26.1 degrees. That's going to be an approximation because our measure of angle B was an approximation. But when I take that and subtract it out, that's going to give me 110.9 degrees. So although we are using law of cosines, we don't have to use it exclusively, especially once we have two of the angle measures in a triangle. We can use the triangle angle sum theorem. I'll go ahead and put that result since that's how we found that third angle measure. Triangle angle sum theorem. And with that, we finalize solving this triangle. Again, we'd already found all three sides. With that last calculation, we have all three angle measures. Let's take a look at a second example in which our triangle does not have any angles given. This is triangle ABC with side lengths 11, 17, and 18. If I mark those for their side labels, this is vertex A on the right. So the side opposite is side A. So it's got the length of 18 meters. Side B is 11 meters in length. And side C is 17 meters in measure. So what I see with this example is I start with all three sides. I start with no angles. And so definitely the versions that we want would be the ones that are solved for cosine of a given angle. So we'll just pick up the one that involves A. So we had just seen it in our last screen. Cosine of A, it's going to be equal to this fraction, B squared plus C squared minus A squared over 2BC. So we'll solve here for cosine or for angle A first. Let's set it up. So cosine of A, again, I'm going to put that because I don't know what the measure for A is, equals, I'm going to leave a space for the inverse cosine in a moment. My fraction is going to be B squared plus C squared. So 11 squared plus 17 squared minus A squared, 18 squared, all over 2 times these two, 11 times 17, which is B times C. We'll approach this in terms of solution just the way that we did our last question. I'm going to apply inverse cosine to both sides to give me back the angle measure. Ultimately, that's what I'm interested in, not so much cosine of the angle, but the angle itself. So inverse cosine will apply to both sides. And that's going to give me an approximate value. Again, I'm going to take that over to the calculator and we'll input it. So I can probably just copy that one and substitute out our numbers here. So our version here that we just set up is going to be 11 squared. Also is actually plus 17 squared minus 18 squared. And then I just need to change these two factors for 11 and 17 is already there. And that's a good just kind of rule of thumb with these laws of cosines equations is you can really use a template and just flip out the values. So I'm going to round this to 76.7 degrees, 76.7 degrees. And that gives us angle A. I'll mark it there. And then I'm also going to mark it here in the diagram, 76.7 degrees. Let's set up for either angle B or C. We could work on either one. Since it's alphabetical, let's work on angle B. So cosine of B, you catch some patterns writing this out. So it always starts with B, and then you're going to have the other two sides first. So it's A squared plus C squared. And you'll subtract the side that you had match your angle over 2AC. Those are always the first two. So again, there's our formula. It's, again, just law of cosine solved for what we specifically need. So we'll set up this one for this calculation. So cosine of B equals, again, I'll leave space for inverse cosine. So A squared plus C squared. So that's 18 squared plus 17 squared minus 11 squared over 2 times 18 plus times 17, times. And then to finalize the solution, just as in our previous one, I want angle measure B. I don't want cosine of B as my final answer. So I'll apply inverse cosine to cancel the cosine function and to give me the angle back instead. And that, again, it's set up. All I need to do is jump over to the calculator and crunch the numbers. So again, I'm just going to pick this up. It's the same template. We're just switching out the values. So that's 18 squared plus 17 squared minus 11 squared over 2 times 18 times 17. And that is giving me, if I round to the nearest tenth, a degree measure of 36.5. So that gets us our second angle measure. We know that that measure of angle B is now 36.5 degrees. We'll mark it here on our diagram. So just taking stock as we do, what's left for me is to find the measure of angle C, and I have completed the solution of this triangle. So again, I could use the third version of the law of cosines, or again, I could use the triangle angle sum theorem, which tells me all three angles have to add up to 180. So a lot of times, if you found two of the angle measures in a triangle, the most convenient is just to take and subtract from 180. So the measure of angle C is going to be equal to 180 degrees. And I'm just subtracting the two previous measures we'd already solved for. So minus 76.7 degrees, minus 36.5 degrees. And that's going to be approximation because those two were approximate. And that's going to give us a measure of, let's go ahead and calculate here on the side since I've got my simple function calculator here. 180 minus 76.7 minus 36.5, and that's going to give me 66.8 degrees. And with that, we have solved our triangle here in this second example. I'm going to highlight those three angle measures again, just to kind of convince myself I have solved it. I've got the three sides, three angles. Our last example involves a question about bearing. So it's a word problem. A plane's flying with an airspeed of 185 miles per hour with a heading 120 degrees. The wind currents are running at a constant 32 miles per hour at 165 degrees clockwise from due north. Our task is to find the true course and ground speed of the plane. So the way we want to approach this question involves the way that we would define this idea of heading. Heading is really a direction in terms of angle that a plane or a car or something that's traveling across the face of the earth would take in order to reach a certain destination. And the way that we define heading is an angle measure clockwise from due north. And so what we got to just notice is that our kind of starting point when we're beginning our measures for heading is north. So what I want to do for this question is I want to draw a diagram. So I'm going to start off with the direction north, and really that's just up. A lot of times we say north is just up. So when I have an initial airspeed of 185 miles per hour with a heading of 120 degrees, I'm measuring 120 degrees clockwise from due north. So 120 degrees is just 30 past 90 degrees. So 90 degrees would be something like a right angle. So we're going a little bit past it. So we'll just mark that as 120 degrees. And we're going to label the actual length of this direction. The technical name for it's a vector. And really what a vector is it's a magnitude that has a certain direction. So the magnitude or the length of this vector is going to be 185 miles per hour. You can think of it as its length as being velocity. So I'm going to mark this as 185. So the plane would have flown in that direction with that velocity if there hadn't been some wind. Now we got to take into account the wind. So the second sentence tells us the wind currents are running at a constant 32 miles per hour. So there's my magnitude for that vector at 165 degrees clockwise from due north. So once I get to the end of this vector, I'm acting like I'm adding them together. So I'm going to start from this right end of my original vector for the plane's travel. And this green vector is going to represent the direction and strength or magnitude of the wind. So it's got a direction 165 degrees clockwise. So you can imagine that 90 degrees would be there, 120 would be there because that would match what we had originally. So 165 is going to be roughly there. Now it's significantly shorter. I'm not drawing this perfectly to scale, but this would have a magnitude of 32. So it should actually be significantly shorter. We can do that. Now, what we need to do with this is form a triangle. So I'm going to just adjust this one so it's more to scale. So we'll say it's got about a length like that. To make a triangle that's going to represent the actual course and direction of the plane, all I'm going to do is connect the endpoints of my two original vectors. So what we're trying to do is we're trying to find out what's the length of this purple side. That would represent the ground speed of the plane. We also want to find some of these angles. We want to find the true course and ground speed of the plane. So ultimately, we're looking for what should I add to 120 from this acute angle in the upper left. So just to mark what we got again, the 185 is for the red line. Let me make sure that's showing up best for the red line. So I'll mark it right there, 185. And the 32 is for the green line. We're trying to find the magnitude and the angle for the purple line. So really it's a question that's similar to one of our laws of cosines questions. We just need to find one more piece of information, and that's either an angle or a side. We always need at least two sides, one angle, or three sides to use law of cosines. And what I notice here is that I can use this angle here. So I'm just going to locate it. This angle here will help me to get to this angle. Because I already know that the angle on the other side there, we had used that was 165 from the word problem. So if I can find this missing small angle, then I can find the angle actually in the triangle. So what I'll do here is I'm just going to use the idea of parallel lines. Those two north directions are parallel, cut by a transversal, that red transversal. These angles, the 120 and the one we're looking for, should be supplementary. They should add to 180. So 120 taken away from 180 is going to give me a measure of 60. And then to find the angle I'm really looking for on the inside of this triangle is 360. That's the full circle minus 60 minus 165. So I'll do that arithmetic here. So 360 minus 60 is 300, minus 165 is going to give me a distance there of 135. So this is now set up, and at this point what I want to do is kind of extract that triangle so that I can consider it without a lot of these markings. So there's our triangle. Again, I'm just pulling it up to the side here so I can label better. I'm looking for this angle right there. I know this one is 135 degrees. Side length of 185, side length of 32. And again, the things we're looking for is that angle measure and that side length. So what I'll do is I'll label these vertices. Let's say that's vertex A, B. In fact, let me give B to this acute one and then C. So then the sides that I've got opposite angle A is going to be 32, B is 185, and C is the one I'm looking for. So it's important to do this because it tells me how it fits into the law of cosines. It's important to label the vertices and the sides with ABC. So if I'm looking for angle A, I'm going to choose the version that starts with cosine A. So that's going to be equal to, remember, you start off with that angle, and then I'm going to go the two letters I didn't use for the sides, b squared plus c squared minus a squared over 2bc. So now that I have it set up and everything is labeled on my diagram, I just need to plug in values. So I'm going to plug in cosine of A. That's what I'm looking for. I'm looking for angle A's measure is equal to, so I'm going to pick up B. B had a length of 185, so 185 squared plus C. So I've run into a problem. I need side C before I can do this calculation. So I'm just going to pause here, and I'm going to run the calculation for side C first. So ... I'll come back there. So I'm going to need to solve for C. So I'm picking up the version that solves with C. Again, I had C in that formula, but that's part of what I'm looking for. So let's solve for that very quickly. C squared is A squared plus B squared minus 2AB cosine C. So let's fill in our values for side C. So that's going to be A squared is 32 squared. B squared is 185 squared minus 2. So then you always multiply times those values to the first power, not squared. So 2 times 32 times 185 times cosine, and I am in luck of 135. And then the last thing to do to solve for C here is take square root. So I'll take square root, and that's what I want to put in the calculator. So we'll solve for C quickly because that's the piece we need just now. So back to Desmos. We'll type it in as we wrote it. So it's a square root of 32 squared plus 185 squared minus 2 times 32 times 185 cosine of 135 degrees. And that's giving me a side length for C of 208.9, 208.9. Let's record that 208.9 as the length of side C. So again, just to place it on my diagram, 208.9, and that's my true ground speed. So 208.9 miles per hour. So if you think about it, the wind is actually increasing the ground speed. Our speed without the wind is 185. With the wind, because it's moving roughly in the same direction as the plane is, it's actually adding to the velocity. Okay, so we found that. What we need to find is the bearing. And what we needed was that value, 208.9. So we'll pick up right where we left off. So plus 208.9 squared minus 32 is my A squared over 2 times B, which is 185 times C, 208.9. And then to finalize this calculation, because I don't want just cosine of A, I want measure of angle A. I'll apply the inverse cosine. It'll cancel the cosine function. And that's ready for us to solve here for measure of angle A. So we got the setup recorded there. Let's take it to our calculator one last time. So I do need to pick up, I'm just going to pick up, well, as a matter of fact, let me just build it. In case you missed where inverse cosine is, it's under the functions tab, trig, in the middle column there. So inverse cosine, and we'll expand our view so we can see it, of 185 squared plus 210 point. Let me make sure I'm setting that up correctly. 185 squared, not 210.5. Let me correct that. That's 208.9 squared. Now we're doing well. Minus 32 squared all over 2 times 185 times 208.9. So it's a big equation to fill in, but ultimately we're good. That's not much of an angle, 6.2 degrees. So we'll head back to finalize that answer. So we'll record what we calculated there. So the measure of angle A, this upper very small angle is 6.2 degrees. And I'll put it on the diagram, but what we've got to note is that that's really not what we're looking for to answer the question. We're trying to find the true course of the plane, the heading. So if I return to my original diagram, ultimately what we need to do is add 6.2 to the original 120. So the way that I would answer this question is that the true course, or the heading, is going to be 126.2 degrees. And the ground speed, which we had already calculated there, it's represented by the side length of C. The ground speed is going to be 208.9 miles per hour. And that finalizes this last example using the law of cosines. Thanks for joining for this investigation of solving triangles using the law of cosines. See you soon.